Okay, the first problem we'll look at in 17.3 is number 4. And we want to determine whether or not f is conservative, so we'll use that theorem we just proved. P and Q are both continuous here. So P with respect to y is 4x, and Q with respect to x is 4y, and they're not equal. So they're not conservative. F is not conservative. Number 6. Okay, P and Q are both continuous. P with respect to y is e to the y. Q with respect to x is e to the y. They're equal, so F is conservative. The domain of F is reals cross reals. X can be anything, Y can be anything, and there's no restrictions on X or Y. Okay, now we have to find the function whose gradient is capital F. So we want del F to equal F. So the partial of F with respect to X should be the first component. And if we integrate this with respect to X, we're going to get X e to the Y plus the constant. Now this constant is not really a constant. It could be a function of Y, because when you take the derivative with respect to X, that'll go to 0. So this derivative with respect to X is 0. Now we take the partial of that with respect to Y, so that's going to be X e to the Y plus K prime of Y, but F of Y was right here. So that tells us that K prime of Y is 0, or K prime of Y is a constant. So our function F is X e to the Y plus constant. Well, the constant could be anything, so let's just take it to be 0. So we have our function to be X e to the Y. And that says that capital F is the gradient of F. Okay, let's look at number 8. Okay, that's continuous for x greater than 0. So our domain is that x has to be greater than 0. Now that's an open, and it's a simply connected set if we stay to the right of the y-axis. So P of y is 0. Q of P of y is 2x. Q of x is 2x. They're equal, so that implies F is conservative. So we have to find the function that's the gradient vector that goes with capital F. So f of x is going to be this first component. We integrate that with respect to x to get f. This is I'm just going to look that up in the integral of ln x in the table. It's that. And then I have a constant with respect to y, because when I take the derivative of that with respect to x, that's just going to be 0. Okay, now I'm going to take the derivative of this with respect to y. So here the x's cancel. I'm doing this with respect to y. That's just going to be x squared plus k prime y. And that's going to equal this function here, because that's f of y. This is f of x, f of y if it's the gradient field. And again, k prime of y is 0, so ky is some constant. We'll just take the constant to be 0, so our function is x squared y plus x ln x. And that tells us that the gradient of f is capital F. Okay, 12. We have to find it and calculate it. So our vector valued function is this. This is f of x, this is f of y. So f of x is y. So we integrate that with respect to x. We get yx plus constant. We then take the partial derivative with respect to y and see that it should be equal to this up here. Well, the x's cancel, so our k is y squared plus constant. We're going to take that constant to be 0. So our function will be yx plus y squared. Now we're going to integrate that. And that's just going to be f evaluated at the endpoints. That follows the fundamental theorem of, I guess you could call it the fundamental theorem of line integrals. If you look, we can use that theorem that says if c is a smooth curve given by the vector function and f is a differentiable function, f is differentiable here, and del f is continuous, well, that's true, then we can use this theorem. So the endpoint of this curve in 12, we have the upper semicircle starts at 0, 1, ends at 2, 1. So this is going to be f of 2, 1 minus f of 0, 1. So we're going to take these and substitute them back in here. So that's 2 times 1 is 2, plus y squared is 1 squared, minus 0 plus 1 squared. And we get 2. Okay. 14. Here's the curve. So R starts at, let's do it this way. Point A where it starts at is where t is 0. So one endpoint where it starts at is 0, 0, and the endpoint that it ends at is 1, 2. That's when t is 1. So this is fx, this is fy. Those are both continuous. We integrate that with respect to x. And so y squared is a constant. That's just the arctan x. Take the derivative. And set it equal to f of y up here. So that tells us that k is a constant. Let it be 0. We can pick it anything we want to. So now we can use the theorem that says that this is f of b minus f of a. So this is f. F is y squared arctan x, evaluate at 0, 0, and 1, 2. So that's going to be 4 arctan 1 minus 0. Arctan 1 is pi over 4, so that's equal to pi. Okay, one more. Let's try 22. I want to find the work. Well, the work is the line integral of the force times the displacement vector. Here, x can't be 0, but if you notice these points are in, let's take the domain to be x greater than 0, and those points are in there, so we're okay. P of y is 2y over x squared. Q of x this is negative, is negative 2y over x squared with another negative, because the derivative of 1 over x is negative 1 over x squared, and those are equal, so it's conservative. Okay, f of x is this. So if I integrate that with respect to x, I'm going to get, that's x to the negative 2, so it's going to be negative y squared x to the negative 1. Take the derivative with respect to y of that. And that's equal to f of y up here. So that's a constant again, and we'll take the constant to be 0. We can take it any way we want it. So our work is just going to be f of b minus f of a, which is going to be minus y squared over x, evaluated from 1, 1 to 4, negative 2, and that's going to be negative 4 over 4 minus a negative, so it's plus 1 over 1, and we get it to be 0. There's no work done. Okay, so this should help you with some of your problems.